All right, good morning. This beautiful Friday morning. Um, we're going to talk about Lab 4, and so we're basically going to finish off Chapter 4, and hopefully start introducing Chapter 5 here shortly. So I've uploaded your next lab and have it due 10 days from now. Okay, we have almost 4 weeks left in the semester, and that's counting the finals week, and we still have an exam and that midterm. I'm supposed to get that out to you all, and then we'll have the final exam, and then another homework. Okay, so we've got a decent amount of work left in the semester. We're going to have two labs left, so we'll have this lab, which what we're going to do in this lab is we're basically going to build the the forwarding logic and the pipeline control logic, okay, and for your pipeline processor, and then the last lab will be basically to put all those components together and build the pipeline data path. Okay, so that one you'll have um, starting on the 27th. I want to have that lab released, and you'll have that lab. Well, actually, it'd be probably the 30th, April 30th, and then you'll have that lab to complete for the remainder of the semester. Okay, so then hopefully you can manage your time wisely there. So anyway, I wanted to spend a little bit of time just going over this lab exercise, and so again, you're actually building the forwarding logic, which is we talked about quite a bit in lecture. Okay, so we don't need to spend a lot of time going over the theory of forwarding, and of course I have verbiage in the lab that kind of explains how that logic should work. Um, but what we're also doing in this lab is we're introducing the pipeline to diagram. So I wanted to spend some time and go through that, and it's kind of a nice um, segue to chapter 5, and sort of we're putting a cap on chapter 4. Okay, so we went over all the theory in chapter 4, and we're going to finish by looking at a real implementation. Okay, albeit very simple, but real nonetheless. Okay. So the diagram looks kind of complicated, but once we walk through it, you'll see that you already understand all of these individual components that are in this diagram. Okay, and so hopefully I can convince you of that today. Okay, so let's start with the fetch stage. That's where, of course, our instructions process, and it starts with the program counter. Okay, and so the PC is in the fetch stage is incremented by 4 and then stored in the IFID register. Remember our register convention. Okay, it's the IFID register because it separates the instruction fetch and the instruction decode. Okay, so we calculate PC plus 4 and feed that into our pipeline register. Okay, and Lab 5 will talk in depth of how to build these pipeline registers. That's mostly what you do in Lab 5 is you build the pipeline registers, and you can start with your single cycle data path and pull components from there. All your muxes and everything can go in there, and you'll build these pipelines or these pipeline registers. Okay, so we won't cover that today, but we'll talk about the theory. And so then, of course, PC plus 4 is also wrapped around into this PC mux. Okay, so that's one of our inputs to the PC mux, and so for normal sequential instruction fetch, we'll just keep incrementing the PC. Okay, and then of course the main goal of the fetch stage is to actually access your instruction memory. And again, we're following kind of a Harvard architecture here, where our instruction memory and our data memory are separate. Okay, and that simplifies things at this level. When we talk about chapter 5, we'll talk about how we actually combine a Harvard architecture into we basically transform it into a von Neumann architecture, so that at the programming level it's von Neumann, and we can and the programmers can take advantage of von Neumann architecture. But then at the microarchitecture level, which is where you're working in lab, it's a Harvard architecture. Okay, the memory hierarchy basically merges those the two together. I'm getting a little ahead of myself because I really enjoy Chapter 5 material, but okay. All right, so that's what goes on. That's really all that goes on in the fetch stage. Okay, um, and then in the decode stage, we grab the instruction that we pulled from memory, okay, from the IFID register, okay, and then we do a number of things. First of all, we feed that into, we break up the instruction just as we did in the single cycle, okay, and feed that into our register file so we can go ahead and access registers, okay, and then we also feed it into our decode unit so we can then extract out um, in, control signals from the op field and the function field, okay. Um, New to this data path, okay, is the pipeline control unit and the forwarding unit. And I'll talk a little bit about what each of those do after we go through this diagram. I'll talk about them in depth, but just from a high level, okay, and we talked about the forwarding unit in lecture. The forwarding unit brings in your RT and RD fields from your instruction, and it grabs the register write signals, okay, from from the execute stage and from the mem stage, okay. And remember, that's so it can compare those and look for data dependencies. What it's doing is it's looking for data dependencies. Okay. It also pulls the use shamped and use immediate field or signals from the decode unit. That's so it knows whether it's using RT or RS or if it's in fact using the immediate and the shamp field. Okay. Now, the output of the forwarding unit is essentially the control signals that control these muxes. Okay, so remember in lecture we talked about split muxes, but then I told you that in lab we're going to go ahead and combine those muxes into two 4-input muxes. Okay, um, and so when I get to the execute stage, I'll talk about the inputs of those muxes. Okay, so again, the forwarding unit uh, basically brings in um, some control signals and your various register specifier signals, and it's looking for data dependencies. And based on those data dependencies, it sets the selection logic on those muxes. Okay. So the other thing that happens in the decode stage is we perform a register read. We also take our immediate value and we either sign extend it or zero extend it depending on the control signal coming from the decode unit. Remember, the decode unit has a sign extension signal, and based on that, we either sign extend our immediate field or we zero extend. Remember, in the case of logical operations like or I and I and XOR I, we zero extend. Okay, but for your arithmetic operations like and subtract and well, actually there is no subtract I. It's an and I. Okay, we sign extend. The other instructions that we sign extend for would be like the branch instructions. Okay. So that comes from your control unit or your decode unit. And by the way, this is the same decode unit that you designed in your single cycle processor. Okay, so we're reusing there. The other thing that happens in the decode stage is we start calculating our branch target. Okay. Now, in this particular pipeline, we could also do that in the execute stage, but the reason I have it calculating the branch target in the decode stage is because in later labs, I would have had you add a branch predictor, okay? But because we had to kind of scale back what we're planning on doing this semester, we're not going to be doing that. But regardless, there's no harm in putting the branch target calculation in the decode stage, because we know we have all the pieces that we need to calculate the branch target. We have the sign extended immediate value, and sign extension is a very quick operation, so we're not increasing our critical path here or anything. And then we also have PC plus 4. Okay, so we take the sign extended output, we shift it by 2, and then we add PC plus 4, and that gives us our branch target, right? You did all that in the single cycle design, except of course you did it all in one essentially one stage, one single cycle. Okay. Um, the other thing we do in the decode stage is we calculate our branch target. Okay, and you calculate the branch target the same way you did the single cycle. Okay, you take your upper 4 bits of PC plus 4, and you concatenate that with the lower 26 bits of the instruction shifted by 2, and that's what we see here. So that gives you a 28 bit value, the lower 26 bits shifted by 2, and then we combine that with the upper 4 bits, which you had some homework problems that kind of had you analyze distances that you could jump. So hopefully that makes a little more sense. Okay, and then we have that as an input to our well, actually, it goes over here, but we have that as an input. Wow, this guy's extra laggy today. I probably should have rebooted it before I did this lecture. So then we have that as an input to our PC mux. Okay. Now the pipeline control unit is new to this design. Okay, so again, the components you're going to design in this lab are your pipeline control unit, your forwarding unit. The pipeline control unit does a couple of things. One, notice it controls this PC mux. Okay, we have a lot more inputs coming from different stages that we need to consider when controlling the PC mux. Okay, so it controls the PC mux, and it controls the IFID register and the ID EX register. Okay, so those are those. Oh boy, I gotta start erasing some signals here because this is just getting out of hand. Okay, I should just use this in pointer mode. I think if I just lightly hover over the diagram, then hopefully you all can see that pointer. I need to check that. Let's see. I don't know if you guys can see that pointer. Hopefully you can. After I've finished making this video, I'll go forward and see that you can see that. Okay, so pipeline control unit, the outputs control the PC mux. Okay, they also control the PC. That's this red signal controls the PC, the IFID, and the IDEX register. Okay, and when I get to the part where I talk about the pipeline control unit, then in depth, I'll go ahead and talk about how that works. Okay, inputs to the pipeline control is obviously the decode. Okay, so it needs to know what instruction is currently being decoded in the decode stage, and based on that, it'll make decisions. And then also feedback from the execute stage. Okay. Okay. Yeah. Here we go. Okay. That allows us to handle branches. So in the execute stage, that's where we resolve the branch, and we know whether the branch was taken or not. And in these labs, you're gonna use an assume not taken strategy. So what it means is you're just going to keep fetching sequentially when you encounter a branch. Well, when the branch comes into the execute stage, then we need to know whether the branch was taken or not. If the branch was taken, then the pipeline control unit will use that information, and it'll use these control signals, okay, to flush your instruction in the fetch stage, and to redirect the program counter to the branch target, which, if you recall, the branch target was calculated in the decode stage, and then it wraps back around here, and it is one of the inputs to our PC mux. Okay. Um, the other thing that the pipeline control unit does is it looks for load hazards. So if you remember, or load delays specifically, if we have a load instruction that is producing a value and then an instruction that immediately follows it that it's consuming it, we have to slip the pipeline. Okay, and so the way we slip the pipeline is we hold the instruction in fetch and in decode, and then we let the instructions in execute, memory, and write back move forward, and then we invalidate the control signals for the instruction going into decode. Okay, so again, we'll talk about how to actually do that when we get to the more in-depth discussion of the pipeline control unit. But that's what the pipeline control unit does for us. So just to summarize, it controls the program counter, okay, and it allows us to orchestrate a refetch when we find that a branch is taken. Okay. Now, if the branch is resolved as not taken, it will just continue fetching sequentially. Nothing happens. So it orchestrates a refetch when a branch in the execute stage is resolved as taken. Okay. When we decode a jump, okay, in the decode stage, it will orchestrate that jump. Okay. And of course, we're also supporting a branch delay slot in this lab, which makes things a whole lot easier. Okay. Okay. So in the execute stage, that's where we have our forwarding muxes, okay? And if you remember, we talked quite a bit about this in lab, or in lecture rather. So for the A side of the ALU, the very first input is our SHAMP field, okay? So we can see that that's pulling instruction or bits 10 to 6, and then it aligns 10 to 6 down to the lower least significant bits of the input of that mux, and then 0 extends. So you should have already had to have done that in your single cycle lab, and then the next input is our forwarding path, okay, from the write back stage. Okay. So we see it's here, and it goes up here and goes in here. And then the next one is the forwarding path from the memory stage. Okay. So the forwarding path from the memory stage allows us to forward from an instruction immediately ahead of us in the pipeline, and the forwarding path from the write back stage allows us to forward from the instruction two stages ahead of us. Okay. And then we're also going to employ that technique I was talking about, where we store the we perform the register write in the first half of the cycle, and then the register read in the second half. So that eliminates an extra forwarding path that we would otherwise need. Okay, so it simplifies our architecture, and it's a very easy change. I don't think I have you do it in this lab, but in the next lab, lab 5, I have you change the register file to be triggered off for the register write to be triggered off of the falling edge of the clock, and that's the only change you have to make to the register file. Okay, the last input to this mux is the register file, the value you read from the register file. And of course, it comes from the IDEX register because the register file was read in the prior cycle. Okay? All right, and the B side of your ALU is very similar, except of course that the first input is your immediate sign extended immediate field. Okay? Comes from the sign extension unit, so it may or may not be sign extended, depending on the control signal. Okay, that sign extension operation would have already happened in the decode stage, so we don't worry about it. It just gets fed right in here. Okay. And again, you're going to control the inputs to these muxes with your forwarding unit. Okay, so you need to understand the inputs of these muxes. So, so if you want, for the A side, if you want the Champ field, the output of your forwarding unit would be 0, 0. And if you wanted to pull from the right back, you want to forward from the right back, it would be 0, 1. If you want to forward from the memory stage, it would be 1, 0. And if you want to pull the value from the register file, it would be 1, 1. Okay, and the B side would follow accordingly. Okay. Of course, also the other thing we do in the execute stage is we run those inputs through the ALU. So of course the control signal, one thing we need to observe is that our control signals are flowing through our pipeline, and yeah, okay, it goes down here and goes into your ALU control. That ALU control is the same one that you designed in the single cycle, okay, and then that feeds into the ALU, okay. Also, if you remember, you had a mux that in your single cycle that selected the destination register, okay, which in this case we're calling write reg, okay, um, for um, for the write back stage, or well, to write into the register file. So now, of course, in the single cycle you had that all in one stage, but in the pipeline design that happens here in the execute. The reason it happens in the execute is because we actually use it as an input to the forwarding unit. Okay, so the forwarding unit doesn't have to be concerned about whether you're using RT or RD as your destination register, because remember, your R-type instructions use RD, and your I-type instructions use RT as the destination register. The forwarding unit doesn't have to worry about that if you put the mux in the execute stage. It just simply looks at the output of that mux and knows that that is the specifier of where the which register is going to be written. Okay, and so it doesn't have to be concerned whether the instruction in the execute stage or the memory stage is using RT or RD as a destination register. It just looks at the output of this mux. Okay. The other thing that's in this pipeline data path, which actually is completely new to you all, I did not talk about this really at all in lecture, is there's a forwarding mux here, okay, and we need to talk about that in this lab. So there is a situation when you have an instruction that a store instruction, for example. If you have a load word and it's loading T0, okay, and then of course there's going to be more to it here. It'll be like T3, let's say. And you have an immediately following store instruction, and I'll just say that's T4, so it's different. There's a data dependency here, okay. The load word is producing T0 and the store word is consuming T0. Now, it turns out because the load word, or the store word rather, is consuming T0 in the execute or the memory stage here, okay, it turns out we don't need to insert a load delay there, okay? And so we can actually forward that. And so this mux in the execute stage is one of two forwarding muxes that allow that to happen. The second one is in the memory stage. Okay. So you're going to need to write that control logic in lab this week. And so one of the signals coming from the forwarding unit comes over here and then goes in here, controls this mux. And then the other signal comes over here and controls this mux in the memory stage. Okay, so what you're going to do is you're going to look and see is the instruction that is producing that T0 is it immediately ahead of me in the pipeline, or is it two stages ahead of me? Okay, we can see for this mux, okay, this particular mux in the decode stage, let's take a look at it. Let's erase this so we can actually see what we're doing here. Okay. It forwards from the right back. Okay. So we can see that. Okay. So because it forwards from the right back, it's forwarding from the instruction that's 2 stages ahead of us. Okay. So if we need to forward from an instruction that's 2 stages ahead of us for the store word, then we'll use this particular mux in the execute stage. Okay. That's pretty much all for the execute stage. So we'll segue into the memory stage so we can talk about this second mux. Okay, again, the second mux is new to us, and what it does is it allows us, it also forwards from the right back stage, but because it sits in the memory stage, it allows us to forward from instructions that are immediately ahead of us in the pipeline. So in this scenario that I've drawn up here with the load word and a store word, this is the forwarding path that we would use for that particular instruction. So what we would do is when we detect that an instruction immediately ahead of us in the pipeline is producing the value that we need for the store word, we would go ahead and set the mux in the execute stage to just grab from its normal path, and then we would set the mux in the memory stage to grab from this path, from the green path, the forwarding path. And actually, honestly, I think as I'm talking it over with you, this would be a don't care. We don't actually care what that mux is set to because we're not going to use its value. Okay. Okay. In that particular scenario. Now, if we had an instruction, okay, that if we had an instruction between these two, so I'm just going to go ahead and insert a no-op here. Let's just say there was a no-op in program order already there. Okay, then we would detect that and of course the forwarding unit is in the decode stage. So when the store word would be in the decode stage, we would look and we would see that ahead of us is a no-op. There's nothing being written there. But then 2 stages ahead of us, there's an instruction that's producing the value that we need. So we would set the muxes, okay? We would set the muxes for this first mux, we would set it to pull from the green path, and then this last mux we would set to pull from the normal path. Okay? So we're orchestrating forwarding on the store word with these 2 muxes. Okay? Now we could have done it with 1 mux. Well, no, we can't. The reason we had to do it, if we tried to use 1 mux in the memory stage, well, at that point the data is already in the register file. It actually left the pipeline. That instruction that we would be pulling data from has actually already committed and is no longer in the pipeline. So the value would have to be read from the register file. So that was why I had to architect it this way. And then, of course, we couldn't put both muxes in the execute stage. Well, could we? I'm trying to think if we could have done this with just 1 mux in the execute stage, because we could pull from this path or. Oh no, of course we can't. Right. The reason we can't do it with a single mux in the execute stage is because we want to be able to forward in this scenario, okay, where we have a store word immediately following a load word. We don't in the execute when the store word is in the execute stage. If it's forwarding from a load word, we don't actually that load word hasn't even produced its value yet. Okay, and that's why we have separate forwarding muxes for the store word, is because it allows us to handle that particular case. And so it reduces a load delay. Now you may say, well, why would you do that? Well, this is actually a copy from memory and placed into another memory location sequence of instructions. So might be fairly common. Okay, and so okay. The other thing that, of course, that happens in the memory stage is we then access memory. Okay. Now, if we're not accessing memory, remember we have a this path around the memory, data memory, which we had in the single cycle, and then of course we have our mem write back pipeline register, and then of course in the single cycle you had this mux which selects between the ALU and the data memory, so that actually goes in the write back. And of course, in write back, we feed back into the register file. Okay, and also notice that the register, the actual register specifier, that tells us which register we're actually going to modify, which is selected with the mux in the execute stage. That flows down the pipeline with the instruction and then loops back. Okay. Likewise, so does the reg write signal. The reg write signal flows down the pipeline with the instruction and then loops back into the register file. Okay? And we talked a little bit about that in lecture. Okay. So as you can see, we've pretty much talked about all of the components in this data path, and so hopefully it's not as complicated and frightening to you at this point. Okay? I'd hate to have made it worse for you. All right. So what I do with the forwarding unit is I get you started, okay, and I give you some skeleton code, okay. Now it was asked of me to go through and talk about the VHDL file and how it needs to be organized. So I thought, well, I'd spend a little bit of time doing that now. I still do want to produce a separate tutorial, like a primer on VHDL, because I think that would be helpful for students. And of course, the beautiful thing about that is I can record it and then I can use it from years from now. And but I haven't prepared for that. I have to spend a decent amount of time preparing for material before I start talking about it. Like I spent all last evening studying this lab and looking at my solutions and remembering how everything's supposed to be put together and all of that. Sometimes it may not seem like I prepare for these lectures, but believe it or not, I actually do. So anyway, when I do that VHDL primer, which I'm hoping to do maybe next week, I keep pushing it off, but it's just busy. Life is busy. Then I'll talk a lot more in depth. But we have our VHDL file, and at the very top, I like to put comments, okay, and kind of describing what this component does. So in VHDL, we provide modularity by breaking our design up into components. So if we go back to our block diagram, we have somewhat broken this pipeline design up into various components. Okay, so for example, the register file you've created, okay, is described in its own single component. Okay, and today you're going to describe the forwarding unit in its own single component, and you're going to describe the pipeline control in its own single component. You've already described the decode unit, the ALU control, or I may call it ALU decode, I can't remember, in their own separate components. Okay, and then you're gonna, in lab 5, the next lab, you're gonna describe this entire single cycle data path as one component. Okay, and the memory and the data, the instruction memory and the data memory are actually the ports to those memories, which we see here, are actually going to be ports to your component, to your data path component. And you already did this with your single cycle, so it'll be very similar to what you did with a single cycle. And then of course your data path component will instantiate all of your individual components that you've built, in addition to describing these pipeline registers and whatnot. Okay, and then of course my test bench instantiates your pipeline component, and it also emulates the memories. So you'll notice inside my test bench, which part of your exercise homework was to go and look at that test bench. You open that test bench, you're going to see how I emulate the instruction memory, for example, and I do so with just a giant table, okay, and the um, entries of those tables are instructions, okay. And then you'll also be able to see the logic of how I emulate the data memory. Okay? Or simulate, actually, honestly, is the correct word. So and I use the term simulate in the test bench because test bench code is non-synthesizable, which means I can't take the test bench code and actually put that onto an FPGA. I can run the test bench code in a simulator, and your uh, single cycle and pipelined components you could actually instantiate in an FPGA. And I wanted to do that this semester, but because we're not meeting in person, that would just be hell for all of us to try to get you all to put it on an FPGA. Now, that being said, if you want to put it on an FPGA, feel free to email me or use the discussion boards I keep talking about. I will gladly walk you through the steps of putting that on an FPGA. It's not that hard. It'd be difficult for us to do not meeting in person, and honestly, I mean the semester is quickly coming to an end, so I just can't get overzealous and whatnot. So I had to back away with my ambitions for this semester, unfortunately. So, but again, if you want me to help you through that process, I'll be happy to do so, especially if you don't feel like you're getting your money's worth out of this class. Another thing, I mean, I don't know, I don't think anybody's ever really taken me up on this offer, but keep in mind I do have about 2 or 3 more additional labs. And so if you really want to continue this work, I'd be happy to help you through the summer and whatnot, continue to progress your processor. So I do this on a daily basis. I love this stuff, and I love mentoring. So again, if you feel like you're getting ripped off this semester, because we're not doing as much, stay engaged with me during the summer, and I'll help you continue to move forward. Okay. Okay, so again, that really was a long tangent, but at the top, I generally have comments that describe the component. The other thing that as you go off and become real engineers, what you'll also put at the top of this is usually a classification sort of statement. Whether it's classified, unclassified, whether it's proprietary, or what exactly this file is. It'll be your marking. Um, and so, is it proprietary? If you go work for a company, you're designing a processor, I can guarantee you that those source files are going to be proprietary. So you'll have those particular markings up there. If you go work for a government lab, depending on what you're designing, it may be classified, unclassified. Um, we have a term that's called OUO, which is like our proprietary. It's official use only. I think other terms, other entities outside of government also use the term OUO. It's basically, I treat it as proprietary, right? So it's not classified, it's unclassified, but it's proprietary. Okay, so you'll have those markings. The other thing you'll have up at the top would be your name. We got to have somebody to blame years from now when you pass this design on. Because unlike your homework assignments, when you design something for a company, it could be used for 20, 30 years, later. I mean, it's reuse is extremely important, and so they whenever you modify that file, whoever last touched that file, usually what they'll do is they'll start with an author list. So you'll be the first author. So you'll have a list that shows the different developers. You'll be the first one, and then if somebody comes along and modifies it later, updates it, then they'll append their name to that list, and then the list just keeps getting appended. Okay. And the reason is there's a couple of reasons. One, to provide attribution. Two, to provide blame. That one's very important. And then three, the main reason is for to look and see who can I contact if I need help with it. So let's say someone inherits your design. So you designed this 5-stage pipeline processor, and then it was used in a product, and then you moved on. Either you moved on, let's say you stayed within the company, and then somebody else came along and they wanted to add a few more instructions, but they're kind of struggling to understand it. They're going to look and see who's the last name on here, and then does that person still work for the company? And if they do, then they're going to go reach out to that individual, which it would be you at that in this example. If that last individual is no longer in the company, okay, they're not going to reach out to you more than likely, especially if it's proprietary code. You can't even. That's what's interesting. When you leave a company, you can't even the future developers can't discuss that code with you even after you've left the company, even though you're the one that developed it because it's proprietary. And once you leave the company, you basically you lose those rights. Okay, so they'll just go down that list and try to find the latest person that worked on it that's still at the company. And I mean, people move around a lot these days within companies. So, or from company to company and within the company. So that's just how you grow in your career. So it's inevitable that developers that worked on this previously no longer work with the company. Okay, and I'll probably I'm almost kind of using this as a practice for the main primer that I'll give, although I'll go in depth a lot more. With Verilog, you have to have these different libraries. Okay, so Verilog, you have to include libraries, just like you do in C. You have include files. That's what these are. So you specify the IEEE library, and then you tell it to use this specific one. Now, you'll notice on your ALU, which I give you the entity. This is all called the entity right here. Okay, this is your entity. For the ALU, I give you an entity, and we have more libraries there because you're doing some arithmetic. Okay, Verilog doesn't really have this concept. And by the way, what I want to do is I want to produce this primer on VHDL and then go and follow it up with a Verilog primer. And honestly, if I teach Verilog, I probably should move on to System Verilog. Um, I'm in the process of learning System Verilog. Well, I've been in the process of learning System Verilog for the last couple of years, but anyway, we're slowly migrating all of our new development over to System Verilog as more and more tools start supporting System Verilog. System Verilog, you can kind of think of it. The way I look at it is Verilog is like C, and System Verilog is C++. So you have a lot more options or constructs that make your code look nicer and whatnot. But anyway, and that honestly, System Verilog is why VHDL is becoming extinct. Is because there is no equivalent. There's no like system VHDL. There's VHDL kind of stopped at VHDL, whereas Verilog is continuing to grow and improve. And so just like you've never heard of any languages like A or B, they existed there because there's a C, there was an A and a B, okay, and there was a D, by the way, programming language. We've never heard of that, and the primary reason is because C took off, and then Strustrup, Bjarne Strustrup, who I actually used to interact with at Texas A&M, developed C++. And so because there was and C++, one of the main motivations behind C++ was maintaining backwards compatibility with C, then that meant that all those other languages just disappeared, and so then C is what we have, and so that's what's eventually I feel like is going to happen with VHDL. But there's still, just like Fortran, there's still a lot of code base written in VHDL, and we're not just going to throw that out and start rewriting in Verilog because of the hours and hours and millions of dollars worth of verification that have been done on those modules. Oh, by the way, I just want to point out that the number of designers to verifiers is usually like a 3-to-1 to like a 6-to-1. And so what that means is that, I don't know if I quite said that right, but what I mean by it is 1 designer to 3 verifiers at a minimum. Okay, So I'm working on a project and I'm the sole designer, and they've got about 3 to 4 verifiers assigned to that project. Okay, so just a heads up, we put a lot more money into verification than we do the design work. Okay, because it's a much harder um, uh, thing to do. Okay. Also, entry level designers usually go into verification first, so they have to get their feet wet with verification, and then they from there they can then move on to the design work. So that's kind of the natural progression that you take. So if you go work for Intel, you will, unless you have a doctorate, you will start with verification, and then eventually you may move on to design. Some people don't move on to design, and it has nothing to do with their abilities. Some people just have a knack for design. We work with some very, I'm sorry, don't move on to from verification because they just have a knack for it. We work with some very seasoned verification engineers that um, they really know what they're doing, and they know the language. They know System Verilog, and they're able to do some amazing things with test benches and whatnot, and what's called UVM verification. And so they're just really good at what they're doing. Okay, and so it would be a shame for them to move out of verification. Okay, and some people just have enough of verification and want to move on to design work. It just depends. Everybody takes different paths. Okay, this is really I'm really going out on a tangent here. Okay, but I'm kind of giving you the ins and outs of HDL design, I guess. All right, so we have our entity here. Okay, so our entity essentially describes our inputs and outputs of our component. Okay, the entity provides the component name, which is in this case forwarding unit, and this is just VHDL syntax. You know, I don't have the VHDL syntax necessarily memorized. I have Verilog syntax a little bit more memorized, but the way I started design is I just start with an old component that I already designed and just start modifying it. Because to remember the exact syntax of this VHDL file, I mean, I don't know. I'm sure there are people, language experts out there that can do that. But for me, especially since I jump back and forth between VHDL Verilog and System Verilog, okay, I usually have to start with a module that I've already designed. And that's why what I do in lab is I give you the entity, or I give you um, a skeleton code. So, and I've got modules. VHDL or Verilog calls them modules, but I've got um, modules um, that I use continually as examples. And the other thing is as I get better at um, VHDL or Verilog, whatever I'm working on, I usually use the latest, unless the latest component or module I did something funky and I'm like, I don't want to do that again. Okay, so I usually have a handful of components and VHDL components and Verilog modules that I feel are really well written, and they're usually ones that I've done in the past. And so I use those as starting points. So I will just open that file. I'll go into the Linux terminal and I'll copy that file to the new name. The file name should match the entity name. Okay. The language doesn't usually require that, but especially for my team, I have it as part of the syntax guidelines. I require my developers to set their file name and the component name to the same. And I do not like having multiple components described in a single file. Okay, it just gets really confusing, and files are cheap. They don't add that much overhead in storage, and it also allows you to build a nice directory structure for your source. And hopefully as I continue to grow these labs, I'd like to actually teach folks how to set up directory structures and repositories and all of that. I was hoping to do that this semester, but that really requires a lot of in-person guidance. So, and so again, and I kind of enforce you to do this in your lab, is you create a file name called forwardingunit.vhd, and it has a single entity. I don't have you merge components into a single file. There is absolutely no benefit to doing that. Okay. Um, so well, okay. Let me take back that comment I said where there's absolutely no benefit. If you are building a library of components, that's where the benefit comes in. Okay, and in that case, you'll have a single name for that file, and then you'll have various components. So if you're building a library of components, then you would deviate from that. But if you're not building a library, I like to have the all each component gets its own file name and the or its own file, and the file name is that of the component name. So again, the entity is the part of the part of the VHDL file that follows the library definitions, and it simply describes the inputs and outputs of our component. Okay. And in VHDL, there are we use the standard logic, and we use standard logic vector. So standard logic is a single bit signal. Okay, so 1 bit wide signal, and standard logic vector is your multiple bits. Okay. And so for use shamped and use immediate, these are inputs, and we know they're inputs because of this keyword in. And so we have the name of the signal followed by a colon and the word in or out if it's an output, but in this case it's an input, so we have in, followed by the type. This is the type of that signal. Okay, we can have multiple signals with different types, okay? And so that's what we have here, is we have a use shamped is an input of type standard logic, okay? And then the order of these does not matter because I have you instantiate your components in such a way where the order doesn't matter, okay? And that was one of the questions that I had for you in lab. Previously, there's two different ways to instantiate a component, and one of them is independent of the order of these input ports and output ports. Okay, and so that's the correct way to instantiate a component. And so when I go over my VHDL primer, I'll talk about that in more depth. Okay, so again, the order doesn't really matter. Now if you'll notice, though, I have the inputs and then I have the outputs, and so your style guide may require that depending on where you go and work. We don't necessarily require it because sometimes, like for a peripheral, we actually want to organize our signals in a different way, not inputs and outputs, cluster the inputs and the outputs together, but maybe what we want to do is we want to have all the bus related signals. Okay, like for example, I'm designing an ADC peripheral right now, analog to digital converter peripheral. So it has a grouping of input and output signals that are used to connect up to the bus, the APB, which is Advanced Peripheral Bus, that is a very common microprocessor bus standard. And then it's got another grouping of signals that are inputs and outputs to the ADC. Okay, input being the ADC channels, and then output being interrupts. So in that case, we like to group our bus signals together, and so our style guide specifically requires that we group bus signals together, and does not specifically require that inputs and outputs be grouped together. If we required inputs and outputs to be grouped together, we couldn't divide things up into functions. So now, for a very simple component like this, the forwarding unit, it's really nice to have your signals grouped into inputs and outputs. Okay, so that's what we have here. And then ID And IDRS and IDRT, those are the RS and RT from the decode stage signals respectively. Those are inputs. So again, we have them specified here. We have a colon, and then we have in, keyword in, which says, hey, this is an input. And this is a standard, these are of type standard logic vector. And then we use this 4 down to 0 to describe the width. Okay, so you'll oftentimes see me use this notation. Okay. Turns out this is this is what Verilog uses, so sometimes I'll use that in text. But they mean the same thing. So it means bits 4 down to 0, 4 to 0. So that's a 5-bit signal, right? 5-bit signal because you have 0, 1, 2, 3, and 4. So you count those out on your hand, that'll be 5 bits. Okay, which makes sense. We know those should be 5 bits because they describe a register, one of 32 registers. Okay, and then we have our reg writes, one from the execute stage and one from the mem stage. And so that tells us whether the instruction immediately ahead of us in the execute stage, what register it's writing to, and the instruction 2 stages ahead of us, which register it's writing to. So again, these are inputs, and they're 5-bit inputs. Okay. Oh, real quick, I didn't talk about these signals and what their function is. They actually tell us whether the instruction immediately ahead of us in the execute stage or 2 stages ahead of us in the mem stage is actually even writing to the register file. Okay, if they're not writing to the register file, if both of these signals are 0, then we don't have a data hazard. We know that because the instructions ahead of us are not actually even writing to the register file. Okay. Okay. Outputs, so ALU source A and ALU source B, okay, these are standard logic vector 1 down to 0, which means they're 2-bit signals. They're outputs, okay, specified by this keyword here. So this is one of the outputs, or 2 of the outputs of our forwarding unit, and they basically they're the selection lines that for the A and B mux of the ALU. And they're 2 bits because remember we have 4 inputs. Okay, so 2 to the 2 is 4. Okay. All right. Now these ones, the last 2 outputs are single bit, so standard logic vector outputs, and they control the mux in the execute stage and the mux in the mem stage for that forwarding path for our store word. So you remember I was talking about that, and so they'll set the muxes of the forwarding path for the store word as I had described earlier in this lecture. Okay, I really don't trust this tool, so I want to take a moment and pause and just make sure that it's recording and everything. Okay, back again. We don't have a lot of time, unfortunately. I've spent a lot of time talking about random things. So, okay, continuing on. So we have we talked about our inputs and outputs. Okay, that's the entity, and then you have the architecture section of the file. And so, essentially, what happens is you can actually have what's interesting about VHDL is you can have multiple architectural sections with the same entity. So if you're implementing for different targets and things like that, you may do that. But we're not doing anything that complicated here. So you have to name the architectural section, the architecture section, because again you can have different architecture sections. And so this name doesn't really matter too much what it is. Like here we just say behave, which is behavioral. It's not a keyword or anything. It's just a name. You could call it arc1 if you wanted to, or arc whatever. And then of course here's your entity name, and you're basically saying this is an architecture with the following name of this entity, or component ultimately. Okay, that's the component name. And then you have a begin and an end. Now, what's interesting is normally right here is where you insert your component instantiations, so or not instantiations but declarations. So if you're going to have a more complicated um, component like your pipeline, will have that where it's instantiating multiple components, then you would put the component declarations there. And in my VHDL primer, I'll talk a lot more about that. The other thing you would put in between the architecture statement and the begin right here is you would also declare all of your signals. Okay, so whatever signals you're declaring. Now, notice, of course, that we don't have anything in this particular um, portion of the uh, VHDL file, and that's because we don't have any internal signals. All of the signals that we're going to use are actually declared in the entity. Okay. Now that's not the case for your single cycle component, and it's certainly not the case for your pipeline component. Okay. But for this case it is. Okay. And then I have insert code here, and it's the forwarding logic for the A side. Okay, so that would be setting ALU source A. Okay, and then I was very generous, and I completely gave you everything you need for the B side. So the B side is actually complete. And so what you need to do for the A side is you need to understand how the B side works, and then copy that and then modify it to do what the A side needs. So let's just real quickly look at the B side. So we're going to use a process block. Process blocks allow us to describe code behaviorally. Okay. In contrast with assign statements that allow us to assign signals and then also component instantiation. So those are different kinds of constructs you might see in an architectural section. Okay, but in this case, we're going to use a process block, and process blocks allow us to use if statements. Okay, and we want to use if statements because we want to encode priority. Okay, and so that's important, and that's also important when it comes to designing the control unit. Okay, so at the top of the process block, we have the sensitivity list, and the sensitivity list has all of the input signals to this particular block of logic. Okay, so for the B side, it's the use immediate, IDRT, EX, write reg, mem write reg, EX write reg enable, and mem reg write enable. Okay, for the A side, well, it's probably going to be, I would say, use shamped and IDRS, and then all of these ones will be the same. Okay, and so again, we're using a process block because it allows us to describe code behaviorally. It allows us to use if-else statements. If-else statements are a lot more intuitive for us as humans to understand than to actually come up with the Boolean logic to do that. You can also describe Boolean logic within a process block, but you can also describe Boolean logic outside of a process block with assign statements. Okay. So usually when I'm describing Boolean logic, I do it so outside of a process block. If I want to use an if-else structure or a case switch statement, then I'll use a process block. Okay. We also use process blocks to describe sequential logic. This is combinatorial logic because it's not based on the positive edge of a clock or the negative edge, whatever edge you're using. It's not based on an edge of a clock. So consult your register file example to see how to describe a sequential block of logic. Okay, that's edge triggered. But you would use a process block for that as well. But this is combinatorial logic, so you can use process blocks to describe combinatorial logic. All right, so the very first thing we're checking, and I described this in lecture, so I'm going to go through this pretty quickly. I've already described this previously. Is we want to make sure we're not using the immediate. If we are using the immediate, then the answer is done. We already know what we need, what our input to our mux needs to be. It needs to be 0, 0, which will grab the immediate value. If we're using an immediate value, there's no forwarding because the immediate value comes from the instruction. Okay, so it's pulled from a portion of the instruction, right? So it's actually the 16 bits immediate field that's either sign extended or not. And that sign extension takes place in the decode stage, which is one stage earlier than where these muxes sit. What's interesting is the logic that we're using to determine the mux selection logic is actually in the decode stage, but then the muxes themselves are in the execute stage and the mem stage. So we're setting things up ahead of time, right? We know that when this instruction gets to the execute stage, the muxes need to be set up accordingly. Okay, so if we're using immediate, there's no forwarding, there's nothing. We just put in the immediate value. So there we have that described. If use immediate, then ALU source is 00. 00 is the very first input to our mux. Okay, else if data is being produced by the instruction one stage ahead. And this is, again, this whole statement has to have priority. The very first thing, highest priority, is it using the immediate. If it's using the immediate, we're done. Well, if we're not using the immediate, then the next question is the instruction ahead of us producing the value we need? Okay, and we talked about this in lecture, how to actually figure that out, but let's just go ahead and look. We look at the instruction ahead. Is the reg write enable signal asserted? If it is, then now we know that instruction ahead of us is actually writing to a register. Okay. The next thing we want to check is, remember, this is talking about the B side of the ALU, so we look at RT and we compare RT to the write reg signal in the execute stage, and so the EX write reg. Okay, and we see we check to see if those two are equal. And then the very last thing we have to do is we also have to check to make sure that that write reg is not set to 0. If it's set to 0, the instruction ahead of us is not producing the instruction we need. Okay. So we're done there if that's the case. Okay, so then if these conditions check out, then we set ALU source to use 10, which according to the diagram should be, that's actually the third input, which is this one, which should be forwarding if I'm consistent with my diagram. Because 10 is this one, which comes down here. Yeah, so that pulls from the stage immediately ahead of us. Okay. And I don't know why I chose this specific mux encoding. It's just what I did. You just have to make sure it matches. You could make that 01 and then just make sure the mux is set accordingly. That's up to you. Okay. All right. So okay. Continuing on. So now, if the instruction immediately ahead of us is not producing the value that we need, okay, then the next thing we want to check is the instruction 2 stages ahead of us. So we want to check, we're in the decode stage right now where we're setting all this stuff. So 2 stages ahead of us is the mem stage. So, and that logic looks exactly the same. We check to see if the write enable is set. If it is, then we know we're writing. Okay. We see if there's a match between our source register and its destination register. If there is, then we're getting closer, and then the very last thing we have to do is make sure that it's not 0. Remember, if it's 0, if we forward and it's 0, we actually will provide an incorrect value to our current instruction. So if it's 0, we need to pull from the register file. So if the register that if the RT register, or well, I have it checking the write reg. You could also check the RT, because if they're equal, it'll match this condition, and then you'll be checking also to see whether, if they're both equal, then if you check the write reg, then you know also the RT field is also 0. Okay, so there's a little bit of flexibility there. And if they're not equal, then you won't even hit this condition and you'll move on, because these are ands, right? Okay. All right. So if you determine that the instruction immediately ahead of you is in fact or not immediately ahead, but 2 stages ahead of you is producing the value, then you would set your ALU source accordingly. And then finally, the fall through is to grab from the register file. So if you're not using the immediate and the instruction immediately ahead of you is not producing the value you need, and the instruction 2 stages ahead of you is not producing the value you need. The fall through is to pull from the register file. And that's it. So you're going to do the same exact thing for the B side, okay? And then you're going to, and so that should be pretty easy. That should mostly be a copy and paste and change a few things. If you understand what I just went through, this example, you should understand how to do it for the A side. The A side looks at RS, and it also uses use champ, so it'll be very similar. And of course, it's going to be setting the ALU source A. Okay. So then the next part is the forwarding logic for the data memory, and that one's going to require just a little bit more thought to it. Okay, and but it's very similar. You're keep a couple things to keep in mind is this forwarding path is only for store word, and store word for store word it only has one source, and that's that it cares about. Okay, so remember RT is the value that you're storing into the register file. RS is the base address, and it turns out that the forwarding logic for the A side of the ALU will take care of the RS part. But for the RT part for a store word, that's what we need this additional forwarding logic here. It's going to look similar. You can use the things you learned from source A and B, okay, but basically you're gonna look and see at the RT field. You're going to compare it to the instruction 1 stage ahead of you, and then 2 stages ahead of you, and then the fall through will be to forward through the normal path. So you'll have to study the data path and understand what those paths are and what you should set those control signals to. Okay? All right, real quickly, I'm going to go over the pipeline control unit, and then I'm going to just go ahead and real briefly introduce part or chapter 5. Okay? So I give you the entity for the pipeline control, and unfortunately it got broken up here across a page boundary, but that's okay, you'll figure that out. The entity tells you all of the signals that you need, and so what the pipeline control unit is doing is it has 2 separate functions. One is to detect jump I'm sorry, load hazard, the load delay hazard, and then the other function is to handle the control flow instructions, okay? And I have a nice little paragraph here that basically outlines what you have to do. And the order in which I describe things in this paragraph is the priority order that you'll have to have. So you're going to use a process block and if statements, okay, and you're going to use those to set your outputs, okay, and the conditionals in the if statements are described in text here. Okay, so I want you to read this and I want you to understand how that's going to work. Okay, so just for example, if a taken branch is detected in the execute stage, the pipeline control unit must flush the instruction in the fetch stage and resume fetching at the branch target. Okay, that right there is your first condition of your if statement. So is the branch a taken branch? So you need to look at your inputs here and figure out what you would use, what inputs you would use here to figure out if it's a taken branch. And then if it is a taken branch, then you need to flush the instruction in the fetch stage and resume fetching of the branch target. You need to figure out how your outputs here need to be set to do that. Okay? And so on and so forth. The next condition is, oh, and then by the way, we don't want to flush the branch delay. We know that. And then the next condition is, the jump instruction. So how do we determine whether whether we encountered a jump? And then we need to set our outputs accordingly. Okay, and so on and so forth. Finally, the pipeline control unit must detect and interlock the processor. So you can have, and what I'm visualizing and what I've done is I have separate logic that actually looks for a jump hazard, and it sets an internal signal that's called jump hazard. Or I'm sorry, I keep saying jump hazard. A load hazard. It detects a load hazard, and I talked about in prior lectures how to detect a load hazard. If you detect a load hazard, then that asserts a signal, and then that signal is fed as one of the last conditions in your if statement. So anyway, hopefully that makes some sense. Start posting stuff to the discussion board if you have questions, and I'll be happy to help you there. Okay, all right. Real quickly, we're going to go ahead and just introduce Chapter 5. That's about all, unfortunately, we really have time for. Um, and so, so anyway, okay. All right, so let me go into full screen here. Okay, so the primary focus of Chapter 5 is memory hierarchy, and this is one of my favorite topics, although I guess every topic seems to be one of my favorites, so just really love computer architecture, I guess. So memory hierarchy is extremely important, and the importance started in really in the 80s, where our memory hierarchy started becoming more complicated in multiple levels. Okay, so and I've got some graphs to show why that is. But the bottom line is that programs demand more and more memory and higher and higher performance. Those are actually those goals are at odds with each other, so they're conflicting goals. If you remember when we first started this semester, I showed you how memory arrays are constructed. Okay, and then I showed you how the individual cells within those memory arrays are constructed. So what an SRAM cell looks like, what a DRAM cell looks like. Well, the thing is as you pack more and more cells into a given memory array, the access time goes up for accessing that memory. So if programmers are demanding more memory and they want higher performance, well, how do we achieve that? Okay, and the answer is with a memory hierarchy. Okay, so larger memories are slower to access, so what's the solution? We have a memory hierarchy here. Hello. Come on. Okay. What is going on? Huh. It's not loading that page. So here, I'm sorry, I'm going to have to pause for a second here. Let's go open that file again. Never really had that happen. Okay. Okay, there we go. All right, so memory hierarchy. Okay, so at the top of the hierarchy we have the processor. Okay, and um, and it runs fast. Okay, as fast as we can. Okay, and so the the memory that the processor directly pulls data from, whether it be instructions or data, okay, needs to be very small and very fast. Okay, it needs to run at the speed of the processor. Okay, so it needs to be small, it needs to be fast, and it needs to be constructed with SRAM. SRAM is faster than DRAM. Okay, and it's more random access, so to speak, and it doesn't have all of the refresh requirements of DRAM and everything, as we talked about earlier. Okay, so we use SRAM. So the processor directly fetches instructions and reads and writes data out of SRAM, very small SRAM. Okay. Now, then it uses larger, slower DRAM for bulk storage. Okay, so when you specify how much RAM your computer has, you're actually specifying how much DRAM it is, how much DRAM it actually has. DRAM is very dense. Okay, and so we're in the gigabyte range for the main memory here. Okay, and but it's very slow. So we use this intermediate, faster SRAM, and that's in the kilobyte range, okay, for directly executing out of, and then we have DRAM for our bulk storage, and then even slower we have magnetic disk or really flash. Servers still use a lot of magnetic disk, but and I have my older HP laptop here that has magnetic disk, but really like the little machine I'm using right now, mobile device and whatnot, is using flash. Okay, and it's much larger in terms of capacity, but much slower. And so there's actually like orders of magnitude difference here. So like your SRAM is 1 or 2 orders of magnitude faster than your DRAM, which is 1 or 2 orders of magnitude faster than your flash, which is then 1 or 2 orders of magnitude faster than your magnetic disk. And servers will often have combinations of flash and magnetic disk. They'll put what they'll do is they'll put like the operating system and component that are accessed quite a bit in flash, and then user storage and bulk data storage will go into magnetic disk. So they develop even a memory hierarchy amongst the file system. Okay, so we use small fast SRAMs to cache. That's the term. If you look up the definition of cache, it's a safe place to keep things, the original Webster definition. We use small SRAMs to cache the data and instructions. Okay, and those sit close to the processor, and they're very fast. Okay, and then as we approach main memory, okay, which is your DRAM, okay, the cache gets larger and slower. Okay, and then DRAM is used for density. Okay, so why do we need this? Well, in the 70s, processors actually executed directly out of DRAM. Okay, so you take the Apple II, which was I think like a 78, 79 kind of time frame, and it had 64 kilobytes of main memory. I think you could get an expansion slot that would bump you up to a whopping 128 kilobytes of main memory. But it had 64 kilobytes of main memory DRAM, and that was small enough, and DRAM and processors were approximately at the same speed, so actually the Apple II did not have any cache. It executed directly out of DRAM. Okay, so the processor directly accessed DRAM. But in the 80s, a whole bunch changed. Okay, in the 80s we started aggressively pipelining. Okay, and we end up with this graph here. So we can see here this is the start. Okay, and we see, so we have performance, and by the way, this is a log plot, and then we have time here. Okay, and so in the 80s, processors and memory ran at the same speed. Okay, in the 70s rather. Okay, they ran at the same speed. Okay, and so we didn't need cache. But then as we progressed through the 80s, we started developing this gap. Okay, between how fast processors can run and how fast memory can run, and that's because we were using very aggressive techniques. The 80s was where we started pipelining a lot, and then in the 90s we started moving to superscalar and out of order execution, and so these instruction level parallelism techniques started really improving the performance of our processors, and then our technology. Our transistors were getting much faster, but then our program space that we required was going way up. In the Apple II, which was the late 70s, 64 kilobytes of memory was enough. If you needed a little bit more, you'd go to 128. Okay. In the 80s, we started needing megabytes of memory. Okay, and then in the 90s, we quickly got to gigabytes. So again, the processor performance was increasing exponentially, and the demand for more memory was increasing. So that led to ultimately a much slower increase of memory speed, okay? Because memory is increasing, memory capacity is also increasing, okay? So this is our memory gap, okay? Memory performance gap, and then we ultimately hit what we call a memory wall, where really the performance of the memory hierarchy is limiting our performance overall. Okay, so that's referred to the memory wall. If you've ever heard that, we kind of slammed right into it. So, okay, a couple of things to note is that this graph, the processor performance levels off, and the reason is this is single core processor, single processor performance. Okay, so in 2005 we actually slammed into what was called the power wall, and I talked a lot about that in the early parts of this class. And so because we slammed into that power wall, single core performance was not increasing. Now, what's interesting is if you actually then plotted this where processor performance is actually the multiple cores. So it starts out single core, and then once we started using multiple cores, then you start including that in this graph. You would either see this do this, you would see it continue at this rate, okay, because now you're increasing the number of processors, okay. You might see something like this in a less aggressive architecture, and then really when we really went crazy with multi-core, you might actually see that performance gap increase even more. Okay, so keep in mind that the reason it levels off is not that processor performance stopped happening. It's because the processor performance of a single core, okay, slowed down. But then we went in. This is the multi-core era. Everything to the right of this line. Okay. So we would see that our required memory bandwidth actually starts doubling and quadrupling as we increase the number of cores. Okay, so it's core dependent. All right. So how do we close this gap? I mean if we have this major performance gap, well, how are processors even able to perform properly, right? Okay. Um, so a little bit more notes about the prior graph. Memory performance is in terms of latency. Okay, so remember we talked early on in the semester that we have the difference between latency and throughput. In this case, we like to use the term bandwidth. Bandwidth is memory throughput. Well, so the beautiful thing about it, part of the reason that we've been able to continue to move forward even with this huge performance gap is the fact that we've been able to take advantage of bandwidth. That we've increased the amount of bandwidth that our memory can provide, and a well-designed memory hierarchy allows us to take advantage of bandwidth. And we'll talk about how it does that as time goes on. Okay. And I talked about the performance leveling off and it being multi-core. So I already talked about that. Okay, so real quickly, this will have to be the last slide today because I'm sure I'm over. Oh yeah. So this is how we accomplish it, and we'll pick back up here next time. But we accomplish it with a memory hierarchy that's made up of multiple levels of cache. Okay, so the level 1 cache, it doesn't matter what class of processor you're looking at, it's all about 64 kilobytes. And that's because that level 1 runs at the speed of the processor, okay? And we really don't see level 1 caches above 64 kilobytes, which, if you remember, the Apple II, well, how much memory did it have? 64 kilobytes of main memory. So the memory that's closest to the processor really hasn't actually changed after 3 or 4 decades. Okay, but what we started doing was adding these additional levels. Okay, and so this particular graph first of all, it's dated. I think 2014 was the last time it was updated. So a decent amount has changed since then, I would say. But the part A of it is your mobile class. Part B is your laptop or desktop, and then part C is your server class. And the machine that I'm actually doing these lectures on kind of sits somewhere between here because it's a mobile device. It's a tablet, but it's a higher performance tablet that also plugs into a dock and becomes a laptop. So there are obviously points in between these three points that we're showing. But and I can guarantee you this guy has level 3 cache. Okay, but they're saying, back then, in general, in the mobile market, you're talking about only 2 levels of cache. Nowadays, I would say it's pretty common to have 3 levels of cache, even in your mobile phone. Okay, so your level 2 cache has about 256 kilobytes of memory. Okay, so it's in the hundreds of kilobytes of memory. Okay, and you can see that it requires about an order of magnitude more access time. Here's the the speed. Oh, and by the way, within the CPU, you actually have registers, right? We talk about the register file. The register file is state of the processor. It's a type of storage, and it's even faster than level 1 memory. Okay, so remember in your processor, if you think back to the critical path homework assignment, you had your I had the register access taking about 90 picoseconds to read, and then your data memory taking about 200 picoseconds. So that's relatively speaking, they're pretty similar, because see, we see register access here is about 300 picoseconds, and then cache is 1 nanosecond, which is 1,000 picoseconds. So anywhere from a third to half of the time to read your registers. Okay, so then and then finally, of course, in your mobile device, you have DRAM for your main memory, and 50 to 100 nanoseconds, and that's pretty accurate even by today's standards. The speeds are actually pretty close to today's standards, because we haven't really improved the latency of memory in the last few years. It hasn't improved that drastically. Okay, now of course 1 to 2 gigabytes is a bit on the low end. Even a mobile phone could have 4 gigabytes, and this little mobile device that's again straddles the A and B line has 8 gigs of RAM. So, okay, and then flash, it's gonna I don't know, that's even your mobile phone will have 64 gigs of flash. Okay, so 64 gigs is kind of the starting point, really. And then this particular machine, I believe, has gosh, I think it's 128 gigs, so a quarter of a terabyte. Wait, is that a quarter of a terabyte? Well, no, it's not. It's an eighth of a terabyte. So I don't remember how much this has, but anyway, you get the point. Okay, and then we move into the laptops, and this is, even though this was in 2012 or whatever, they are saying, hey, a lot of laptops nowadays are using flash memory, so that's your solid state drive. Okay, and that is true, and desktops as well, and then of course what they've introduced is a third level of cache. Now, what's interesting is, though, if you look at the level 2, it still has about the same size and about the same access time as up here in the mobile market. So really, the difference between a mobile processor and a higher performance desktop processor in terms of the memory hierarchy is they just added another level. They kept the other levels the same. Okay, and that is true. Because of the access time of memory. So, between the A class and B class, you're not actually dealing with faster, larger memory. You're still stuck with the same process technology. Okay. All right, and then of course here, yeah, I mean, that's pretty accurate in terms of RAM. That hasn't really changed a whole hell of a lot. Okay. All right, and then we go into the server market, and our registers run a little bit faster. Server, you're going to be dealing with i7s and whatnot, not your i5s that you might find in your desktop or laptop. And then like this little mobile guy is an M-Core, which is, I think it was roughly equivalent to like an i3. Okay, and we also have a third level of cache. Notice the level 1 and level 2 are the same as the other two, but the big difference here is how spacious the level 3 is. Okay, in the server market, you're going to have a much larger level 3. And as we're going to talk about, the other thing that changes from the B class to the C class is the number of cores. Okay, and what we're going to learn when we talk about memory hierarchy is that your level 3 is distributed amongst all the different cores. Your level 3 is actually where your shared memory happens. So when you share memory amongst cores, it's happening at the level 3. Okay, it's the last level cache. If you only have 2 levels of cache, then it's happening at level 2. But in a modern processor architecture, it's happening at the level 3. So you're sharing amongst your cores at the level 3. Okay, And so that's why going from the desktop class to the server class, the amount of level 3 cache increases. And that's because the number of cores is going to increase. And as you increase the number of cores, you're going to increase the amount of level 3 cache you have. Because each core is usually allocated a certain amount of level 3 that it has ownership of. Okay? We'll talk about that towards the end of chapter 5 is how shared memory happens. Okay, and of course the other thing that changes drastically between A class and B class is the amount of DRAM, and this is probably pretty accurate. I just bought a server for about $5,000 for work that has 90 some gigs of RAM, but it's expandable up to like 760 some gigs of RAM. Okay, so, but I obviously didn't fill it out because that would cost probably $20,000 to fill all that RAM. But the point is that this is still pretty up to date when it comes to that amount of storage, and same for the flash. And the other thing is of course with servers is it's going to have a mix of flash and magnetic storage. Magnetic storage is still very dense compared to flash. Okay, and so your bulk storage on a server is still going to be magnetic disk, and you'll probably map like the OS and your different applications in flash. The other thing is keep in mind flash still has a max read-write cycle. So in other words, in server terminology, it has a dependability and reliability issue. Okay, so it actually wears out. So you really don't want to be reading and writing to your flash as much. So that's why mapping the OS and different things into flash is um, pretty safe bet because you're not continually modifying operating system files and things like that. Whereas for user storage, that user storage is constantly being modified. Okay. Well, unfortunately, that's all we have for today in terms of time. I could go on for hours. I'm all pumped up on this stuff, so I'm going to go into work and do some architectural work. So hope you're enjoying these lectures and hope you're staying healthy and happy.